Morning, everyone. So over the last 2 days, we've been looking at organic compounds using the lens that organic compounds will typically have many different isomers. I pulled out a nice chart here that actually separates for you the different types of isomerism we've seen so far. The word isomerism here, it has that prefix here, iso. Iso means something is the same about them. For us, our isomers here are actually all going to have the same molecular formula. They're going to have the same number of carbons, same number of hydrogens, but something is different about their structure or the orientation that makes them actually different isomers. We started off separating isomerism into two types, structural isomerism or stereoisomerism. For structural isomerism here, something is physically different about their bonding. And we found that for structural isomerism, to make sure we didn't accidentally miss a structural isomer, I would encourage you to start off with the longest chain. Let's do pentane again here. I'm going to do a skeletal structure. A skeletal structure here has every corner actually refers to a carbon bit. Every kink here is going to be a C. So that's going to be pentane. And all we did is, starting from the longest chain, we started slowly shortening the chain. What if I break off this first carbon on the end here? That would be equivalent of a methyl group here. The question here is, where can I put that methyl group here back on my butane? So my butane here would just be 4 carbons long here. Notice that we can never put methyl groups back on the ends, or else that's just going to lengthen the chain again. That's just going to be a pentane. What we can do is we can actually put it sort of mid-chain here. Structural isomers will have totally different names. This guy here is called 2-methylbutane. You can even try 3-methylbutane later on, but based on our counting rules here, that would also be 2-methylbutane. That would be the same. Then you shorten the chain a little bit more. Let's cut otherwise another methyl group here. Then I would have just a propane. In this case here, I have only two choices. I can't put methyl groups here on the ending. I'm going to put both methyls on the carbon in the middle, and therefore I get 2,2-dimethylpropane. They have a different name. There's going to be different terms of London forces as well. Something that's long and straight chain like this will have a lot of axis point, a lot of surface area, lots of exposure, whereas something like this is sort of kinked in on itself like a soccer ball here. The London forces might be slightly weaker. So that was the case of structural isomerism. Definitely as the molecule gets longer, the number of isomers increases quite dramatically. Then what we look at here is what's referred to as stereoisomerism. Stereo refers to something about their 3D geometry is actually different. We're not actually breaking bonds and reattaching them. Everything is still attached in roughly the same order, but something is different about their angles. So this stereoisomerism here, we've mainly focused on what are referred to as configured isomers. As we start talking about EZ and RS, we'll review those. But before we do that, there's what's referred to as a conformation isomer. A conformer here is essentially, I mentioned this yesterday, it's basically, we know for a sigma bond, overlap along the internuclear axis, we know there's already free rotation. So for example, if I take a molecule, let's take ethane. Let's say I have fluorines on my ethane. Because this one here is a single bond, that one there allows for free rotation, this is going to be one conformer. What if I actually had the fluorines actually on different sides? So what if I had this picture, it's implied the rest of them are just hydrogens. Well, in this case, I didn't need to break any bonds, and because the single bond allows for free rotation, it's just a matter of just flipping this around, and suddenly the fluorines on the bottom. These two are conformers of each other here. I haven't actually created anything different. The types of configuration isomers that we talked about here was, no, they actually are different. We still would have to end up breaking bonds. In this case here, the types of bonds that we're breaking, they're either the single bonds in a ring. Typically, we're having to break maybe even pi bonds to switch from one to the other. So let's just swap this up here. Let's switch it up for an alkene instead. An alkene similarly can have the fluorines on both sides, or I can have the fluorines on opposite sides here. Remember, it's otherwise H if I don't mention it here. In this case here, because a double bond as well as a triple bond, because this one here is rigid, this one here, remember, is a sigma bond and a pi bond. Although the sigma bond would have twisted, the pi bond, which is overlap above and below the plane here, if I manage to actually twist those pi bonds, I'm actually breaking the pi bond to try to interconvert from one to the other. So this is actually two different isomers. All the bonding is the same, double bond in the middle, and then both holding a fluorine and a carbon. But down this branch of a configuration isomer, something is different about their 3D orientation. This is referred, at first, we had used the cis-trans notation. So looking at the carbons involved in the double bond here, if they both hold a same group, they both happen to hold a fluorine here. If those same groups here are on the same side, we would refer to them as cis. We found that that was a little bit limited because then we have to have the same group. We then identified using the Kahn-Ingold-Prelog rules here. We actually did it by priority. If the priorities were also in the same orientation, we actually refer to this one here as the Z isomer. Z is on the same side. If they were across from each other here, like in math class here, this would actually be a transverse. This would be a cross. So this is at first just a trans isomer. If these were the high priority groups and they were also across from each other, we call them E for entgegen, and entgegen actually means opposite of each other. I'm going to show you a molecule later on. Although cis is usually going to be Z, that correlation here is not always the case. So just check each molecule one by one. Then what we did was the hardest one here, optical isomerism. The only real difference is how they actually influence optical light, how they rotate the plane polarized light. This is where we got into RS isomerism here. I'm going to give you a few practice questions so we can do this here, and then we'll see a diagram of what it's actually doing. So just as a quick warm-up here, let's just try out a EZ orientation. So let's try carbon, double bond. Let's put a CH3 group on this side, CH2, CH3. Let's make the other ones here CH3 and a hydrogen. I'm going to give you a maybe a hexane ring here. I'm going to put a iodine on top and iodine on the bottom here. So we have those two. I want you to identify E or Z. Just practicing R and S as well. Let's try out. Just get used to seeing these sort of tetrahedrals. It's always going to be a chiral carbon. So it's a carbon that's connected to 4 different groupings. Let's put a hydrogen. Let's go up here to a fluorine. Behind the page is going to be a chlorine. And then in front is going to be a bromine group. I'm just randomly sketching these, so I don't know what's going to end up happening. So carbon, let's put a, sorry, it can't be a double bond. Let's go a single bond OCH3. Let's put a Cu group. Let's go down to a iodine, and let's go forward to a methyl group. Okay, so all of these ones here are types of configuration isomers. There's something that's restrictive. In most of these cases, the restrictive part here is the double bond that actually doesn't twist, or the ring doesn't flip itself. So these two are practicing for EZ. The other two here are dealing with chiral carbons. Whenever we have an asymmetric carbon, a chiral center is whenever a carbon has 4 different neighbors, we assign the priorities, point the lowest priority group here away from us, and depending on clockwise or counterclockwise, we can say R or S. So I'd encourage you just to pause the video and try it out for yourself. As we look at trying to identify the isomers and naming these ones here, at first for the double bond, we can start with cis-trans. Oh, good. These carbons here that are involved in the double bond, they both happen to hold a methyl group. And both of those methyl groups happen to be pointing above the double bond. So this is actually the cis isomer. Cis is a prefix that comes right in the beginning of the name. We saw that cis was a little bit archaic of terminology here. What you can do is you can actually assign priority. The easiest way to assign priority is just looking at the element number. So carbon is element number 6, hydrogen is element number 1. The high priority group is up. This time when I have a carbon, this one here, they both have a carbon on the end, so I can't decide on the first chain, then go to the next one. The next one out would be a hydrogen, where the next one out is going to be a carbon. So that gives you a nice conclusion that longer chains of, like, let's say these carbon, hydrocarbon tails here, longer chains are actually going to be a higher priority. You notice the high priority groups are actually pointing different. Here's an example where we were cis, we were actually having the same group on both sides, but this is actually the opposite orientation. Let's see if we can name the rest of this molecule here. We still want to find the longest chain. So that's going to be 5 carbons long. I want to count from the side, so the double bond takes lowest priority. So 1, 2, 3, 4, 5, and on 3 there's a methyl group. So while I have cis or E, the rest of it is going to be, I have a 3 methyl. That's going to be the methyl branch off carbon number 3, and then off of carbon number 2, there's a, it starts off with a double bond. You can say 2-pentene. More commonly, we say pent 2-ene. The double bond starts from 2 over to 3. That is the name of the geometric isomer with the cis and the E in front. How about this ring here? We know it's going to be a cyclohexane. The ring doesn't allow for any free rotation. So even though they're not necessarily, these I groups aren't actually side by side, you see that one I is up, one I is down. That's also opposite orientation. That also refers to the E orientation, opposite. So as I name this group here, I can call this ring part here cyclohexane, and then I have a 1,4. So let's do this here. 1,4 dichloro cyclohexane. There's still two different isomers of this. Are the two I's all both pointing to the same side of the ring or opposite side? Because they're opposite side here, we can say E, 1,4 dichlorocyclohexane. Okay. Don't forget that cyclo part here because that reminds me it's in a ring. Then the harder type of isomerism here, again, these are called chirocenters. We assign the priority just like we did before. So just by element number, bromine's highest, then chlorine, then fluorine, then hydrogen. Before you deal with clockwise or counterclockwise, I want you to point the 4 group away from you. So right now my 4 group is actually going to the left. I want you to imagine taking your eye and actually looking at it from this angle. When you look at it from this angle here, the bromine would be in front of the page. It's going to rotate counterclockwise to chlorine and then counterclockwise to fluorine. Because this one here is counterclockwise, let's say CCK, counterclockwise here is actually going to the left. So this is actually the sinister. It's actually S, whatever the rest of this molecule here is. Bromochlorofluoromethane. Okay, but that's the S isomer. How about on the other one here? You might need to actually draw these functional groups to actually decide for yourself here. I is going to be the highest atomic number. Even though the Cu group is very important, this is just a carbon where this is already an oxygen. So the oxygen here takes the win, second priority. Then I have a Cu group, C bonded to 2 other oxygens, then C only bonded to hydrogens. This is my 3. This one here, unfortunately, is my 4. So this is exactly the opposite orientation that I want because the 4 group is actually pointed, I'm on the wrong side. The 4 is actually pointed towards me. So I want to imagine walking around to the other side, actually looking at this alkane from the opposite orientation, and actually looking from this side. If you just sort of do a perspective diagram here, you should see that the 1, 2, and 3 end up forming a clockwise orientation. Clockwise here is actually the R isomer. Okay, so just get some practice with identifying the different priorities, trying to see it from different sides. Clockwise for the molecule is R, counterclockwise for the molecule is S. Then what we did towards the end of last class was we actually looked at what is a physical property that might be different between R and S. We can actually look, we talked about plane polarized light here. Ordinary light here is actually an electromagnetic field that actually comes to us in a spiral orientation. We put it through a filter or a polarizer of some sort. Essentially, it only lets light come in with one orientation. Right now, everything is vertical. Let's put our R isomer in here, or our S isomer. If this was not optically active, if we were vertical coming in, we would expect to be vertical coming out. But what's ending up happening here is because the R isomer here is optically active, this one here will actually twist the plane polarized light. Instead of being vertical, it might twist it in the counterclockwise direction when I'm actually looking this way. Or if I have S instead, S does the opposite and it's actually going to twist in the opposite orientation. So be careful there. The molecule itself, we had already identified clockwise or counterclockwise. That is unrelated to whether this angle ends up being clockwise or counterclockwise. This in biology ends up giving you D sugars, L sugars. It actually refers to which way it actually directs plane polarized light. Optical isomers here do change the angle. Depending on the deflection, I can figure out sort of the concentration and sort of which isomer that I have. Some reactions only use the R isomer, some only use the S isomer, so it's important to tell which hand that we're using. We had referred to a racemic mixture. What if I put in an equal amount of R and S inside? So R might want to twist it one way, S might want to twist it the other way. A racemic mixture or a racemate. A racemate is going to be a 50-50 mixture of R and S, and therefore one twisted, let's say 20 degrees to the left, the other twisted 20 degrees to the right. Overall, it's not going to be optically active. So that's another way that optical isomers do not actually reflect plane polarized light. While we're talking about isomers, just for completeness sake here, mainly we're only going to look at one chirocarbon at a time, especially as you do get into the biochemistry and do get into having many chirocenters. You will always have a chirocenter whenever carbon is bonded to 4 different neighbors. Right, so you can identify priorities there here. What they've done is they've actually put a star beside the chirocarbon. So this time I have a molecule with 2 chirocenters. Let's say for argument's sake here, both of these are R. Okay, we have this word here, an enantiomer, and enantiomer is a perfect mirror image of each other. It's like your left hand and your right hand. If you put a mirror in between here, the CHO and the CH2OH, those parts don't change. Those parts can twist in the single bond, no problem. But for the chiral carbons, for the ones that are holding 4 different groups, anytime you take a mirror, it actually has converted all the R's to an S, right? So these two are mirror images of each other. I'm opposite R and S at each chiral center. Well, what if I compared it? What if I have another molecule which was S in one, but actually R in the other? Still a different isomer, because at this chiral carbon, this is R and this is actually, oh, this is R. This one here is S and this is R. So they're actually different. The more general term is a diastereomer. When I have multiple chiral centers, some of them are mirrored and some of them aren't mirrored, they're all referred to as diastereomers. They are only referred to as enantiomers if they are a perfect mirror image of each other. Okay, so hopefully that's a nice overview of the different type of isomerism that we've been seeing. The next section in this organic chapter, we are going to start looking at reactions of organic compounds. This is where organic chemistry gets really fun. And we're going to slowly work up to it today, introducing just alkanes. So if you can just pull out your notes page here on alkanes. What do we know about alkanes so far? Alkanes only contain C's and H's, right? These ones here, you can refer to them as hydrocarbons. Of course, later on, you can actually substitute other groups in that would actually give it different behaviors. So hydrocarbons, we're looking at the whole compound being saturated. Saturated meaning you're actually holding the maximum number of hydrogen attachments. So therefore, everything is single bonded. This word here does have to do with saturated fats. Saturated fats are long chains that are all single bonded. There's no multiple bonds in sight. And alkanes had this general formula. Remember, every carbon has the equivalent 2 hydrogens, except for the 2 carbons on the end. They have 2 extra. This is now referred to as general formula for your alkane. So these ones here, we're going to see alkanes, why we're starting with them. Alkanes are actually fairly boring. They're actually very, very low in reactivity. Why is that? Well, when we start looking at carbon-carbon bonds and carbon-hydrogen bonds here, the CH and CC bonds, table, I believe it's table 11, will give you these bond enthalpies. How much energy do you need to actually rip these bonds apart here is actually very, very high. You actually need to input in a really high source of energy here. So let's just write here, hydrocarbons. Hydrocarbons only react in the presence of a high energy source. We're going to see later on in this lesson here an energy source like UV light that's going to be energetic enough. Or the first examples we're going to see is, well, when I have a burning reaction, so if I have a combustion reaction, well, although I might need to provide it the activation energy just to get it going, well, it's just going to release so much energy here. That's going to be enough to actually start breaking bonds. So outside of a high energy source like UV or outside of combustion, alkanes are actually fairly inert. CNH and CNC are not very polar. If you look at the electron activities, definitely when carbon fights against carbon, there is no difference. Carbon and hydrogen, I believe the difference is a difference of about 0.4. We have been saying, yeah, carbon does win by a little bit, but not enough to be a dipole. So sure, it's not a perfect 50-50 split here, but it might be like a 49-51 split, okay? We're going to see other groupings later on. It's due to their dipole, it's due to having a partial positive and partial negative that actually makes them susceptible, makes them vulnerable to attack. In this case here, they're not polar at all. So these ones here are not susceptible. They're not vulnerable. They're not going to react. Not susceptible to attack by many common reagents. Okay. So the conclusion here, I want you to just take away from this section is alkanes have low reactivity. Okay, so they do react, but only in really stringent circumstances. Okay, in those cases, alkanes are slightly boring. In other cases, they're actually fairly exciting. So when we actually take a look at burning reaction, we can actually see different ways we can make the alkane burn. So alkanes are flammable; they can combust. Combustion will always require oxygen. It's going to yield for complete combustion carbon dioxide and water. These ones here can be used as different fuels. So nicely here for our automobiles, we typically use like C5 to C10. Those ones there are liquid fuels, so they are alkanes. Because their bond enthalpies are so high, they actually store a lot of energy. If I can actually harness that energy, I can convert it into more useful forms. So it can be used as fuel. We use it for cars. We use it for cooking. Sometimes you have gas stoves. Right, that can be very exciting. Okay, so let's have a look at different ways of balancing this. So you've already learned how to balance equations for complete combustion. We're always assuming complete. Complete combustion refers to you have enough oxygen. Right, the fire's been burning for a while here, and all of it gets burned up. So let's just start off with propane here, common fuel used in barbecues or portable stoves. Yes, for enthalpy of combustion, when we did this in chapter 5, we had a pesky little 1. So basically, you're not allowed to change this one. The nice thing about a combustion is all the carbon is going to end up in the CO2 product, and all the hydrogen is going to actually end up in the hydrogen. So this one actually separates the carbon from the hydrogen for us here. And we can actually just count, well, if I have 3 carbons, I would need to have 3 CO2s. If I have 8 hydrogens, the hydrogen come to us in pairs, so I would need a 4 there. I would always balance the oxygens at the end because oxygen is its own element here. If I put a number later on, it just matches the O's for me. I just care about the total number, so 3 times 2 makes 6 O's, plus these 4 are 10 O's. If O's come in pairs, I would need a 5 here. Sometimes you're dealing with a pesky little fraction, so be it. You notice that the enthalpy of combustion is actually quite high. Combustions here are exo. You can bank on that. Aside from you sparking the reaction and providing the activation energy, it ends up giving off a lot of energy to the environment. Okay. Octane is a very primary component of gasoline. Let's practice the combustion here. You do the same thing. Let's say I want to burn just 1 mole of octane, so that way it's an enthalpy of combustion. C8 means I fully burn it to 8 CO2s. 18 H's means I need 9. The problem here is I'm going to have an odd number of oxygens. 8 times 2 is 16, plus the 9 here is 25. I can deal with the pesky little fraction, that's okay, 25 over 2. If this were not an enthalpy of combustion, which has to be defined per mole, so this one here is defined per mole, which means that this one here has to be a 1. I would usually scale this whole thing up. 2, 25, 16, 18. Right? Whenever you balance these equations, you can always assume it's complete combustion. They're just adding in here, well, what if the combustion were actually not complete? So complete combustion requires a large oxygen to fuel ratio, tons of oxygen around versus the fuel that you have. If I only have limited oxygen, maybe it's been burning for a long time and I've been using up the oxygen, when there's limited amount, we get what's referred to as partial combustion or incomplete combustion. Instead of fully getting things oxidizing to form the full CO2, we're actually going to end up getting just COs, or sometimes even just amorphous carbon solid. The carbon is actually, let's say, so we actually get solid particulates. Right. This one here, if it were in a nicer form, it could be our graphite, it could be our diamond, whatever. Usually it's just amorphous. Usually it's just a random orientation of carbons here. Because it is solids that are sort of burning off here, this will give rise to a dirtier smoke or dirtier flame. So it's going to be a little bit darker. You're going to see unburned carbon off of this one here. So that could be a multiple choice question. Well, what if I have incomplete combustion? What could I expect to see? Just note that aside from the CO2, you might see COs, a poisonous gas, or carbon. And in this case here, if I actually write this out for you, you can actually balance it. So you can say, okay, well, I have 3 carbons here. Well, I would need 3 carbons there. 8 hydrogens. Again, 4 times 2 make 8. I have 3 O's and 4 O's. I have 7 O's. The O's still come in pairs. So this one here would be 7 over 2. So we can still balance it in the same way, but that assumes incomplete combustion. Okay. Let's be careful, especially with incomplete combustion. Not only is it going to be a dirtier smoke and a dirtier flame here, in general, the CO is actually a poisonous gas. So we can actually make a note here. CO is a colorless, highly toxic gas. So if we're worried about sort of our cars burning gasolines and producing a bunch of COs, we have what's referred to as a catalytic converter that actually converts CO into a little bit more stable and a little bit safer form of CO2. So this all happens when I have a less than optimum. So I have not enough oxygen to burn the amount of fuel that I have. So in this case here, we can say at very low concentration of oxygen, we end up getting CO, like I said. Carbon can also be produced, and depending on which product that they want for you, I can still balance it here. Let's take our propane again. Let's burn it with oxygen. The oxygen comes to us in the diatomic form, but it just turns out there's not a lot of oxygen present in the atmosphere, and therefore it just becomes solid carbon. We're still always just going to simplify things and assume that we do get water. So really it's just the carbon that's different. This is going to end up giving you 3 carbons. 4 times 2 make 8. 4 oxygen, so I would need a 2 there, and there we go. We balanced it. This one, again, the emphasis here is this is a solid. So there's just 2 questions here, just practicing a little bit of review from our chapter 5, thermodynamics. So they give you some bond enthalpy data here. Estimate the heat of combustion for propane. You're going to always assume complete combustion. Assume we fully get CO2 unless otherwise specified. And then they start talking about here, okay, we're going to have on our table 13, table 13 has a bunch of heats of combustion. You should be able to find both propane as a source and octane as a source here. Both of them have a certain, if you burn a particular mole of this chemical here, how much energy is released. It's actually adding an added avenue to this based on the density. You might need to look up that one there. But based on the density, you have to carry this gasoline to your camping site here. Just because one might produce more energy, maybe based on the density, it's actually heavier, so you may not actually want to carry that. So it's just sort of introducing to you, when we start thinking about fuels, it's not just talking about this is the energy per mole. I also want to start thinking about based through density. So look up the density, depending solid, liquid, or gas. Okay, based on the density, I actually want to do something like energy per volume. If you do the energy option with me here, that's going to be called an energy density, or you can say the energy per mass. I need to carry it. That's referred to as a specific energy. So it just introduces another element as we're talking about burning fuels. Okay. So just one more page here. Turns out when we actually dig gasoline out of oil reserves here, it comes to us as crude oil. Crude oil is a mixture. It can be anywhere from carbon 1s all the way to carbon 200, maybe even longer than that. Obviously, I need to purify it somehow. So what we actually do is we actually use what's referred to as a fractionating column to actually separate them. Here's what happens. We actually heat to vaporize all chemicals. So take everything, all the short chains and long chains. Let's have the heat source down here. Let's put it all in the gas state. The heat source is still going to be, well, it's hot when it first enters this part here. As it rises, it's going to steadily cool down, right? As it cools down, though, so it's going to cool down as the gas rises. As it gets farther and farther away from the heat source, depending on my length of chain here, the carbon 1s and carbon 4s, so methane down to butane, these ones here are actually gaseous even by room temperature. So I had already made them a gas here. Those are going to float all the way to the top. What about C5 to C8? Well, what's the difference? Well, C5 is starting to get a lengthier chain, 6, 7, 8, right? Again, a lengthier chain here. Although they are all alkanes, although there's no polarity here, we are all relying on London force to keep us together. As you get more atoms, I would expect more charges, more background attractions, so therefore the London force actually increases. So you can make a note here. All only have London forces, a type of van der Waals forces, which gets stronger as the chain lengthens, as the chain gets longer, right? So therefore, if I have longer chains, these ones here will have higher boiling points. So the ones that are lengthier chains, C30 to C70, as it gets only a little bit away from the heat source, it's already cooled down enough that it actually passed through its condensing point, its boiling point. It's actually going to start liquefying. As a liquid, it can then be just tapered off. And they're actually giving you a few pictures of what do we use each of these fuels for. If I'm a slightly shorter chain here, those can rise a little bit, but again, I can fractionate them. I can pull them off at different layers. Usually, we'll see in our energy section here, we are mainly interested in the C5s, C10s, because those give us our fuels for everyday transportation. These ones here are going to be liquid fuels here. Again, they would arose different amounts away from the heat source, and they can actually get tapered off. Between diesel fuels and regular petroleum gasoline fuels here, diesel fuels typically are a little bit heavier, and more heavier automobiles would utilize them. Okay, so that's one way we can actually separate them. Remember, for being in a homologous series, they show a gradation in physical properties. Okay. One more interesting reaction I want to just end off with. So alkanes, pretty much we've been looking at, well, they're unreactive aside from combustion. Yeah, we had a complete combustion, incomplete combustion. They do participate in the second type of reaction. Under other sources of high energy light, I mentioned UV as an example, it actually does react. So this is sort of reaction number 2. Although they don't readily react with most compounds, most other reagents, in the presence of chloride and bromine, they do participate in a substitution reaction. Substitution reaction here, as the name suggests, it gets substituted. We trade one for the other. Here's the overall that they talk about. So methane, in the presence of chloride, it actually is going to substitute. A chlorine has actually swapped in and a hydrogen has actually moved out, so it's HCl like this. But this one here will only occur in the presence of UV light, which actually gives us a really good test for whether we have just alkanes or alkenes. Let's pretend I have methane in here. So maybe I bubbled methane underwater. I have a little bit of methane there. That's an alkane. Let's compare it to an alkene. An alkene here, simplest alkene, would at least have 2 carbons here. In this case here, we'll learn later on the alkene reactions. You can toss in chlorine or even toss in bromine here. This one here does not need UV light. The nice thing about these ones here is it has a corresponding color change here. Usually chlorine is a yellow-green gas. If there's no traces of it left over, it means something reacted. Whereas for an alkane, only in the presence of a high energy source, as we're going to see what the high energy source does, it actually initiates, it actually triggers the mechanism. This one here only reacts under at least a pulse of UV light. It doesn't need to be a constant UV radiation, but we're going to see what the UV is doing. This one here is referred to as a free radical chain mechanism. So free radical chain mechanism. You do need to know this mechanism here. It's not too hard. First step here is called an initiation phase. We're going to take our chlorine, or our bromine is a little bit safer to work with. The initiation phase is actually the one that needs a pulse of UV light, high energy light. And what's going to happen here is the UV light actually brings so much energy. I know a bond is 2 electrons. What I'm going to do is I'm going to use all this UV light and I'm going to separate this bond here. We're going to actually have, very fancy name here, we're going to have something called photochemical homolytic fission. We briefly ran into this term here, homolytic fission, back in our bonding chapter. Let me just recap it with you here. Photochemical means we're using a light source to homolytically, to separate, so this one here means break, but break it in an even fashion. If I have 2 electrons, let's break 1 electron back to each neighbor. What we're going to do is we're actually going to introduce different electron arrows. When we do electron arrows here, we always point to what the electrons are doing. I know there's 2 electrons here. Because there's only 1 electron that's doing it here, I'm going to do a fish hook, so a half arrow going this way and a half arrow going this way. If later on I have a full arrow for electrons, that actually refers to both electrons doing the change. This one here is only 1 electron. So 1 electron goes back to each neighbor and ends up giving me 1 chloride radical on the left and 1 chloride radical on the right. It's been perfectly evenly separated. That's the part that actually needs UV. The rest of it can actually propagate no problem. So it's an even splitting. So we end up producing here a chlorine radical. Be careful here, this doesn't mean chlorine positive or chlorine negative. It's actually not charged, it's actually neutral, but having that unpaired electron here makes it very unstable. So what's going to happen here is it's actually going to come in, it wants to substitute in place of the hydrogen. So this bond here, also made out of 2 electrons, the hydrogen is going to use this 1 electron. Again, we have a fish hook. Fish hook just refers to 1 electron actually doing this change here. We end up creating H is now going to be bonded with the Cl, and it leaves me here with the methyl radical. So we have a methyl radical here. Now it's the methyl that actually has the unpaired electron, and now methyl is ready. The reason why we call it a propagation is because it's ready to continue. What's going to happen, although at first I needed UV light to completely rip this in 2, this methyl radical here is going to use its 1 electron, again half arrow. This one here we call it a fish hook. I'll write that down for you here. Fish hook implies just 1 electron movement. Okay. whereas we're going to do double-headed arrows. We're actually going to do double-headed arrows more often in this chapter, but we'll deal with this one first. So with the fishhook, this one here can actually trigger another chlorine to break up, again another fishhook, and we're going to end up getting methane now with the chlorine substitution, and I have recreated this chloride, right? So you see both reactions require these free radicals, and all we haven't really introduced is how come I refer to it as a chain mechanism here. A chain mechanism, almost like a catalyst. Basically, I had a chlorine go into the reaction. A chlorine destroys one of the bonds from a hydrogen. Notice that the chlorine radical here gets regenerated later on. Now the chlorine is ready to attack again. So what could end up happening here is it could be to the very same methane molecule. So methane started off here with being a CH4 like this. In the presence of a chlorine under UV light, again, the UV was needed to just trigger this reaction to initiate it. Basically, what I started doing is I actually swapped on the chlorine here. So at first, I have now a chloromethane, right? And then I have a HCl like this. And this could happen again. Well, if one of these end up forming a radical again, I can end up putting in another chlorine. So with another chlorine neighbor here, maybe this chlorine here switches itself in, and we end up getting CCl2 or CCl3. We can get any numbers on this one, or this can attack other methanes as well, giving rise to a whole bunch of different things. It's called a chain mechanism because this one here goes back in to do the reaction again. Now, it's not all doom and gloom, however. This one here does not continue indefinitely here. There are what's referred to as a termination step. A termination step here involves getting rid of our radicals. Well, just like the chlorine radical here could have ran into another methane molecule, chlorines could run into each other. This one here would terminate and then just reform chlorine. Now it's in the diatomic form, now it's more stable. The chlorine radical here could actually run into the methyl radical. When I have an unpaired electron plus unpaired electron, it ends up forming just a single bond, and therefore I get another chloromethane. And to a very, very trace amount here, because we didn't create a lot of CH3 to begin with, but it's possible for a CH3 to actually run into another CH3, and therefore what we'll end up having is a slightly longer alkane. This one here only produces, so only, we refer to it as a trace amounts. Trace amounts means very little. This is not the best way of making a longer alkane from it, okay? So far, we've learned two different types. Alkanes in general are very unreactive. Their bonds are strong. You need a high energy source like a combustion. We've done complete combustion, the burning with a lot of oxygen, partial combustion, forming carbon and carbon monoxide, and we did this free radical mechanism. See if you can practice this one here. Try using bromine instead, and see if you can follow along what's the initiation step, propagation, and termination. We'll pick it up from there tomorrow. Thanks, guys.